research in my faculty member here to strengthen the publication, especially from the national journal or international journal. We have a lot of the collaboration research with the other country in over the world, like the USA, Dutch, and Asian country, and also in Australia. We have collaborated in recently in to research together and publish together. I think this very important to work together. And recently we have doing the accreditation international in our program study in Aquas from Germany. So I think this event is very, very important. We have one cluster specialist in language education this year. We have the site visit from Germany, and also maybe in the next year we have to propose other program study to earn the international accreditation. That's again that I would like to thank you to Professor Neumann, and I hope the other the next activity we have to strengthen our activity in teaching, learning, and also in research together. Hopefully, thank you very much. As a dean. In general this afternoon. Thank you.
Okay, thank you so much, Bapak Dr. Hartono MA, Dean of Faculty of Teacher Training and Education, Universitas Sriwijaya. And now, without further ado, we'll hear the general lecture from Professor Dr. Knut Neumann. And these sessions will be led by our moderator, Bapak Suhandri, PhD. To Bapak Suhandri, PhD, time is yours now.
Okay, thank you, Bu Dwi. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, ladies and gentlemen. Welcome to our general lecture today. I'm Suhendri, lecturer of Physics Education Department, Faculty of Teacher Training and Education, Universitas Sriwijaya, will be your moderator in this session. Firstly, I would like to say hello to our speaker. Hello, Prof. Neumann. How are you?
Good, thank you. Good afternoon.
Good afternoon. Thank you. Nice to meet you, and thank you for being with us in this general lecture. Ladies and gentlemen, before we listen to Prof. Neumann presentation, I would like to inform you a short CV curriculum vitae of our speaker. Full name, Professor Dr. Neumann. He is a professor in Department of Physics Education, IPN, Leibniz Institute for Science and Mathematics Education, Germany. His education background, he completed studies in mathematics and physics at University of Düsseldorf in 2000, and then completed state examination for the teaching profession at gymnasium in mathematics and physics at University of Düsseldorf, also in 2000, and finished his doctorate degree in physics education in University of Education at Heidelberg in 2004. Professional activity, now he is head of Department of Physics Education, IPN, Leibniz Institute for Science and Mathematics Education since 2013, and as deputy head of the Department of Physics Education from 2009 to 2013. He was also managing director of the Center of Empirical Research at the University Duisburg-Essen, and also research scientist at University Duisburg-Essen and at University of Düsseldorf. His research interests, among them, diagnosing abilities in physics, development of abilities in physics while attending school, physics teacher professional skill and their development, and identifying the supporting talented physics student. Now he involved in a number of projects such as the future of STEM learning, idea factory for classes with digital media, identify development in physics, mathematics and science for life, exploring learning in various approach to teaching energy, the development of professional competence in pre-service mathematics and science teacher education. As a professor, of course, he has many publications in articles and books. That is all the brief CV of Prof. Knut Neumann. More information maybe will be introduced by Prof. Neumann next. Okay, ladies and gentlemen, we have about 1 hour and 15 minutes. So maybe for the first 1 hour, we for presentation for Prof. Neumann, and then in the 15-minute last for the question and answer session. Okay, Prof. Okay, all audience, let us welcome our distinguished speaker, Prof. Knut Neumann. Prof. Knut Neumann, Zoom floor is yours.
Thank you very much, and good afternoon again.
Good afternoon.
I think 60 minutes works very well to speak about new directions of physics education or for physics education research, teaching and learning. And thank you for the very nice introduction and the very nice overview of my work. I'll highlight some of that work throughout the talk, but will give you a more general idea of what I think are the challenges we're facing in physics education research, the limitations that we have in what we know as a field and what we don't know as a field, and you know, like the issues surrounding these like major deficits. And I accordingly structured the talk in 3 major parts. I'll begin by talking about like what are the current challenges, not just the challenges we're facing in physics education or science education research, but what are the challenges that we are facing as societies in the 21st century or at the beginning of the 21st century, and why would we want to do physics education, and in this context, what can physics education help address these challenges, and what is the current situation of physics education? I'll then move on and show you a little of the research that I think has been done in the field. Obviously, there's a broad range of different types of research and research foci that have been addressed in the past 2 decades, I'd say. I'll focus on those that I think are the most important ones with respect to the challenges we are facing, and I'll discuss what we know, and I think we already do know a lot. But there's also things we don't know, and that needs to be tackled in the future that is coming. And then there's the third part where I'll focus on issues that I think are surrounding these like bigger issues that are smaller but need to still be attended to because they matter for the overall problems. So what's the world looking like at the beginning of the 21st century? I think essentially, if you take a step back and you're looking at the big picture, the world has changed, right? We're essentially entering a new epoch. We're moving from the age of industrialization and post-industrialization to what is generally called the Anthropocene, where we're seeing a major change or major changes in the across the Earth as a result of humans interacting with the Earth and like expanding their work. These changes have begun with the industrialization in the 1800s, but and I'm sure you all have seen the figures have increased exponentially since the 1950s. And there's a whole lot of challenges, like very immediate challenges that we are facing that are resulting from from the fact that essentially humans have conquered the Earth, if you want. And the some of them are obviously climate change. We are seeing an increasing number of fires. We see floodings, we see droughts across the world occurring in different places. Just generally, the climate has changed, and so has the weather. The weather has become more extreme. Just look at the number of hurricanes that have hit the United States, for example, in the past couple of years. And well, we're also facing, and in a way that is connected, we're facing a huge crisis with respect to energy, because we know that if we continue producing energy, and as a physicist, it's always hard to say produce energy, but from a societal view, we need energy, right, as a society, and the energy production that we've been following so far, that majorly build on non-renewable energies like coal, oil, and stuff, is intrinsically linked to climate change, right? The carbon dioxide emissions that are resulting from energy productions are driving climate change in a way. So what we are facing in terms of an energy crisis is the fact that we should actually reduce the consumption and production of energy, speaking in everyday language, on the one hand, but on the other hand, we all have an increasing number of electrical devices that need to be powered, and so we're needing more energy than ever, especially in the developed countries. And well, it's not just energy that we need food, we need produce, any kind of produce. So what happens is we're moving from farming, for example, that is focused on small types of farms, towards like mass productions of meat, of produce in general. And the what happens as a result is humans are trying to turn more and more of the rainforest, for example, into farmland, and that results not just this, right, but this particularly results in a loss of biodiversity. And with the increasing population in the world of more than 7 billion people now, and the limited number of natural resources, there's a lot of more challenges that we are facing, including the assurance of clean water supplies, food security, managing diseases, the pandemic, if you want. All of these things have changed the world, and they've changed how we live. And we need to address these challenges if we want the world to exist as we know, or continue to exist as we know it. And the issues are more pressing than ever. And in order to address these challenges resulting from human-induced climate change, environmental impact, it is very important that we need to understand the impact of science and technology on the world, and what can be done, how we can use science and technology to change these things, right? And so as a result, the scientific thinking, or teaching students scientific thinking, is fundamentally important for individual, community, and global decision making to mitigate the impacts and adopt to a more sustainable practice. And this means that we essentially need two things, right? We need future researchers and technicians on the one hand, as a result of science education. That is, scientists and technologists who can help address these challenges. We don't expect every single citizen to be able to address these challenges, but we will need scientists and technology engineers, essentially, helping us address these issues. And on the other hand, we still need educated citizens who are literate in science, who understand the role that science plays, both in taking us to where we are right now, and essentially paving the way for the challenges that we are facing, and at the same time as a means to address these challenges. And one core aspect of science education is that students develop a decent competence in physics, right? If you're thinking about the challenges, think about the energy crisis. Without a deep understanding of how energy is produced, right? And knowing that it is in fact not produced, but it's transformed from one form of energy to another form of energy, and that different forms of energy have different values for us. And what it means to have renewable energies versus non-renewable energies, and why it's so difficult to serve like a whole country drawing on renewable energies, is something that is fundamentally linked to students' understanding of the energy concept, for example. And there's many other things, right? The understanding the climate system requires you to develop a good understanding of physics, because a whole lot of the processes that are going on in the climate system, in the Earth's weather system, are based on physics concept, like condensation and evaporation, different times of different flows of energy and matter throughout the Earth's system. And understanding these issues will help understand and address the challenges, either if you're interested as a student, I'm sorry, as a future researcher, or at least as an educated citizen, so you're able to make informed decision and understand political decisions about these issues. The problem, and that's the actual, that what I just outlined is the vision, right? And the reality of science and physics in particular looks completely different, right? While we need more researchers and engineers, what we are seeing is that the number of sufficiently competent students that would be available as a workforce for physics researchers, science researchers, or engineers are staying the same or at best rising very slowly, right? While the need is increased tremendously. This is a figure from a German research institute, right, that shows the development of the need of a competent workforce versus the availability of a competent workforce. And what you're seeing is there's an increasing gap, right, between the workforce that's available and the workforce that's needed. And on the other hand, we know from studies, international large-scale assessments, such as PISA, for example, that there's a high number of students in Germany, and obviously Germany already has a very developed education system. About half of the students would count as either not sufficiently competent or barely competent with respect to making informed decisions in their everyday life based on their understanding or competence in science or physics specifically. So essentially, the issue we're facing is we need more students, we need more physicists, we need more engineers, we need more workforce in STEM, but what we are seeing is numbers are declining. Fewer and fewer students are choosing physics when they're allowed to choose, right? So that means that we are seeing a decrease in the number of students going into the area of physics while we need more, actually. And the other thing is we are seeing that an increasing number of citizens fail to understand the most basic processes underlying the issues we are facing as a society, hence they can't make an informed decision. Obviously, research has acknowledged this, right? And it's not that this is a new issue. This is known for maybe 10, 15, maybe 20 years with the first PISA study already. There were a lot of warning signs and issues flagged by researchers, and it has gradually moved into the focus of attention of the society as a whole and politicians in particular, and that generated for many countries a situation in which there was an increasing amount of research or money available for funding research into the underlying issues. So it's not that we are unprepared. There's a whole lot of ideas and how we could tackle these issues in physics education and how physics education, teaching and learning of physics can actually help address these issues. And one of the ideas that have been developed is that other than it was historically the case in physics education in many countries, where physics education was about students learning the physics and a broad range of like physics knowledge. Nowadays, what we want them to develop is not just knowledge, but competence. Competence meaning that students have a well-connected knowledge organized around the core concepts, right? So they're no longer supposed to learn everything you can potentially learn about physics, every teeny tiny detail, but they need to have that knowledge that kind of enables them or represents a deep understanding of the core concepts of physics. So they can see a challenge, they can assess the situation, they can understand what the challenge generally about, right? If you think about the informed citizen, you don't want the informed citizen to watch a TV discussion about the pandemic nowadays and be a virologist or epidemiologist, right? And understand the exact processes that are going on in terms of infections and stuff. But you would want them to generally understand why it makes sense or make not sense, in which situation it makes sense or does not make sense to wear a mask, for example. So they will understand, you know, why there are certain recommendations, and they'll obey the recommendations, not just because it's the law, it's there's a fine if you don't do it, but they understand why it helps actually counteracting a pandemic. And this involves deep understanding of some core concepts of physics, right? Such as you know, an exponential distribution or an exponential development of a system, and systems thinking, for example, thinking in terms of, you know, like how do systems interact with each other and so on. The second thing that competence entails is the abilities and skills to engage in the practices of physics, right? So that means not just having the knowledge, even though it's a well-connected knowledge, but be able to use this knowledge to ask questions about the world, to create a model of a phenomenon, or to carry out an argument about a certain claim, for example, about climate change, right? And last but not least, a third thing that is very important for competence in physics is motivation. You know, motivation to engage in these problems. It doesn't help if you know all this stuff and you know how to do it, and you can use your knowledge to fix the problem potentially, but you don't want to, or you don't care, right? So there needs to be a certain level of motivation to look at the problem through a physics lens, from a physics perspective, and the willingness to engage in understanding the problem, modeling the problem, finding a solution to the problem. And that's been referred to in the past as motivation, and is nowadays often referred to more generally as physics identity. And I'll talk a little more about the identity concept later. And that should enable students to understand and explain real world phenomena and solve related problems. That's the overall goal, right? We want students to, in everyday language, we want students to understand what's going on and be able to address issues that they identify in their everyday lives using their competence in physics. And that can be anything from understanding that your local shop tries to screw you on, you know, the car repair because your car is actually not as broken as they try telling you, up to addressing the energy crisis and understanding why it makes sense to be careful with the use of the resources that we are having. So why we should not waste energy. Funny enough, even though it's conserved from a physics point of view. So the question is, how do we develop this kind of competence? How do we help students, or how can we help students develop this kind of competence? Obviously, this is not something you can teach in the sense that, you know, this is 3-week physics unit, and then afterwards students are competent in physics. This is, or requires, a coherent effort across years and years of teaching, essentially across students' whole physics career, right? So a lot of the research in science education and also in physics education has focused in the past decade on understanding how students develop this competence as in a sense of, you know, sorry, a well-connected knowledge organized around the core concept, how students develop the skills and abilities needed to engage in the practices, and how students develop the motivation to engage in physics. And the theoretical construct that has been used to describe this type of like development of competence are learning progressions, right? Learning progressions are supposed to describe how students develop an increasingly elaborate understanding of a domain or an increasingly elaborate means of engaging with problems through the practices of science or physics more specifically, right? And the general idea of a learning progression is that it has like a lower anchor, which kind of represents the knowledge, skills, or abilities that students have when they're entering the learning progression. And then you have an upper anchor, and the upper anchor represents what students should be knowing and be capable to do with that knowledge when they're leaving school, right? And then the learning progression is supposed to describe a series of intermediate steps between the lower and the upper anchor that are supposed to guide instruction in grade bands and even individual grades, so that teachers know, you know, where can I expect my students to be at a certain grade level, and what is the kind of knowledge or the kind of like abilities and skills that I need to teach them in order to support them in moving to the next level within that learning progression. And the idea is that learning progression can in a way help address this issue that there's a certain disalignment between the educational goals and what curriculum, what teachers are actually teaching, right? Because if you're looking at Germany, for example, you know, we do have this vision of students developing competence for, you know, like 15 to 20 years now. But when you go into a classroom, what you're seeing a lot is teachers teaching business as usual, as they always did, right? They're still teaching that unit on optics in grade 7 with no particular vision of how that fits into supporting students developing this overarching competence, right? And then a lot of assessments, especially in countries that are building on standardized testing. A lot of these standardized tests are not at all aligned with any idea of how students progress towards developing competence in physics, and instead are just simple multiple choice tests that are testing a broad array of knowledge. So this disalignment of curriculum and assessments with the overall educational goals are a major issue and have sparked an increasing amount of research on developing learning progressions for the core concepts of physics and the core practices of physics and science more generally. So what does a learning progression look like? I've done some work on learning progressions myself, so I want to give you an example for a better understanding of how I think this work can inform and already does inform physics teaching and learning. I've been working, amongst other things, on developing a learning progression for energy. As I've said earlier, energy, I think, is one of the core, if not the core concept of science, right? It's not just important in physics. It plays a major role in essentially every science discipline, but it's particularly core to physics, right? Physics in energy and physics allows us to address almost any problem can be solved by building on this idea of energy conservation, right? And applying the principle of energy conservation. And we can understand a lot about what a system can do, cannot do, and how long it can do it by understanding the flows into and out of a system and the energy related processes that go on within a system. So from a physics point of view, what students need to learn about energy is obviously they need to understand how energy is conserved as essentially the endpoint, if you want, while it changes its forms of appearance, how it manifests in the world through either transformation from one manifestation or one form into another, or how it transfers in one form from one place to another. And that in these two processes, transformation and transfer, whatever happens, some of the energy is always transformed into well, heat or thermal energy of the environment, and dissipates into the environment and is no longer available for further use. So some of the energy during the processes of transformation or transfer is degraded, despite the fact that the total amount of energy in an isolated system is conserved, right? And especially these two things that appear, these two last issues, degradation and conservation, these two aspects of students' understanding of energy are critical to understand, how real world phenomena, real world problems or processes differ from the idealized processes that we often tend to hypothesize when we are trying to solve physics problems. The problem is that at the other end, at the lower anchor, really what we are seeing is students having all kinds of everyday conceptions, right? They're connecting energy to living, right? To activity. Oh, I don't have a lot of energy today. I think I'll go to bed again. Or I'm exhausted from exercising. I need an energy drink. Funny enough, most energy drinks don't even contain energy because there's 0 calories. But they're still energy drinks, right? And that's confusing students. And then students understand that as a society, we need energy. Machines need energy to work. Our computers, cell phones, and well, a lot of the devices we're using in our everyday lives nowadays need energy so that they can run. But all of these understandings that students develop from their everyday experiences are not necessarily they're not necessarily congruent with the physics understanding, right? So the question is, how do students develop this this understanding that I've just been outlining as an upper anchor from these everyday understandings that they bring when they come to school at the lower anchor. And oops, sorry. So what we've been doing in our work, we've been trying to develop a model, right? And this model has identified these 4 aspects of energy: forms and sources of energy, transfer and transformation of energy, dissipation and degradation, and then conservation of energy, essentially as 4 aspects, right? And we have hypothesized that students would develop an understanding of energy by first developing a knowledge, an increasingly complex knowledge of forms and sources, right? So they're learning about one form, they're learning about another form, and like by identifying patterns across how these forms apply to the world, they're building an increasingly complex knowledge about this aspect, right? They're beginning to understand what it means that there is an energy form, and they might begin to understand that a form of energy is not an ontological thing, but that a form of energy is a way that energy manifests in the real world. Think about kinetic energy, right? Which manifests in objects moving. But it's not fundamentally different from potential. Well, it is fundamentally different from potential energy in the sense that kinetic and potential energy are 2 different things from a physics point of view, but it's not fundamentally different from the energy that is stored in something. It's actually the same energy. It just shows up in 2 different forms. So the idea that we were having is that students would develop an increasingly complex knowledge about these four aspects, and that they would begin understanding, would begin by developing a knowledge of forms and sources, and then later they would start developing a knowledge about transfer and transformation, dissipation, degradation, and conservation. And I just need to look at the okay. At the time, I'll speed up a little and move through this a little quicker to save some time, because there's other things I want to talk about, and these are a lot of technical details that I brought because I thought some of you might be interested in details. If you have questions about this, you can always ask them in the question and answer sessions, or I'd like to refer you to the papers that we've been writing about it. So the first thing we did is we tested this model, and what we found is that, as you can see here, we found that indeed, this aspect of forms is easier for students to understand than the aspect of conservation. I don't know why the label disappeared here, but right. And then there's somewhat of a messy middle in between. So moving from forms through transfer and transformation, dissipation, which are essentially going together, right? So it seems that students already develop an initial understanding of dissipation when they're developing an understanding of transfer and transformation. And then at the very last, and that seems to be the hardest bit for students to understand, is this idea of energy conservation. And this is a smooth plot, obviously a fitted plot of where students are in grade 6, 8, and 10. And another thing that is obviously very interesting in this context is, if you're looking at this, at the end of grade 6, a majority of the students would be able to understand energy forms and some parts of transfer and dissipation. And then towards grade 8, more students, students just move on generally, right? So you could say that the majority of the students has developed mastery of this aspect of forms and maybe even of transfer and dissipation, transfer and transformation, and dissipation and degradation. But even in grade 10, only about 1/3 of the students really has developed mastery of this idea of energy conservation, which is very well in line with the literature. I'm sure you're familiar with the work of Reiner Stewart, who was at IPN as well, my predecessor essentially. In the 1980s, he already had evidence that students really struggle to get to this point of understanding energy conservation. So that's definitely an issue that in physics education research we need to more closely attend to. Why are students struggling to developing this understanding of energy conservation? What is so hard for them to understand? And I think one of the issues that is so hard for them to understand is it contradicts their everyday experience, right? Because in everyday experience, energy is not conserved, right? Because why do I need to recharge my phone if this energy thing is conserved, right? And at best, students learn the energy principle as in they're memorizing it, but they're not able to use it to explain problems because it's essentially contradicting the everyday experience. One thing that we could not confirm in this model is this idea that students are developing an increasingly complex knowledge about each of these aspects, right? It just didn't turn out that way for different reasons that I don't want to delve into. So what we did is we reconsidered our model, and I'm more or less showing this to show you how this type of work works, right? You're not developing a learning progression, then you're done, right? You're constantly and continuously refining a learning progression up to the point where it actually helps you connect the everyday learning that happens in classes to this overarching progression of how students develop understanding of a particular core concept of physics, right? So we went back and we looked at the model and we were thinking, well, honestly, this idea of thinking about these like boxes, forms and sources, transfer and transfer as silos in which students develop a knowledge, that's actually not true. Because if you think about it, in order to be able to understand transfer and transformation, you know, or learn about transfer and transformation, you need to have a situation in where different forms of energy are converted from one into another, right? So in a way, an understanding of a certain level of knowledge about forms and sources is a prerequisite for learning about transfer and transformation, at least for meaningful learning about transfer and transformation, right? Because you can, for example, learn, and I've always met a teacher who would tell me, well, I can teach my kids in elementary school the conservation of energy. And then when you talk to the kids, you know, they tell you, oh, energy is conserved. And then you're like, well, what does that mean? And they're like, well, I don't know, but the teacher says it's conserved, right? So we're saying it's conserved, right? So it's essentially what happens is you can teach energy conservation as a fact, where if you ask students and you ask them like, is energy conserved, yes or no, they'll say yes. Or if you ask them like, what about energy? You know, like what's the core feature of energy? And they're like, oh, it's conserved. But then you ask them, what does that mean? And they're like, well, we don't know. There's a very famous example, you know, where you have a person dropping a stone. And then, you know, the students are asked to describe this process, and they can correctly argue that all the potential gravitational energy you're having when you're holding the stone up is converted into kinetic energy. And then when the stone lays flat on the ground and you're asking, like, where's the energy? They're like, well, now it's gone, right? There's no energy anymore. So obviously they're struggling to make sense of this. And we think, or we hypothesize, this is a problem that is related to the fact that that students are taught about these aspects in isolation from each other, right? They're taught about conservation, but the knowledge they have about conservation is not gradually built by them understanding forms and sources and how they're transformed into each other, but rather that they're just told energy is conserved. So we had this idea that you know, what's underlying this progression that we are seeing, that students progress from an understanding of forms and sources over transfer and transformation, dissipation and degradation to conservation, is actually corresponding to them building an increasingly complex knowledge across these boxes. So we teamed up with one of the psychometricians at IPN, and I don't want to go into the details because it's really like psychometric stuff at this point. As I said, you can ask me about it or read up on it in the respective papers. So what we did is we kind of tested this assumption of a knowledge integration model underlying students' progression, you know, them learning about forms and then learning about transformation between forms and then learning about more forms and so on. And we can actually show that this assumption is better supported by the data than either a pure knowledge accumulation model where students are just learning about energy in the individual boxes, and they're learning more about forms, more about transfer and transformation, and so on. And we also tested against an unconstrained model, you know, just to generally see if, well, you can obviously fit any data to any kind of model. So we wanted to have an idea of like, you just fit a random model to the data, how well does that fit, right? And does the other model actually fit significantly better? And we find it does, right? So we assume that underlying this progression in students' understanding of energy is a knowledge integration model. And the I need to hurry up, I think. Oops, sorry. so the resulting idea, as I said, right, like the implications for how you would want to teach energy is that you need different forms of energy, but you're not teaching all the forms in grade 6. It's more like a pyramid, right? You're beginning to teach one form of energy, maybe kinetic. You're teaching another form of energy, for example, gravitational energy, and then you're introducing students to the transformation between these forms, right? And then you're teaching or introducing more forms, and once you have more forms, you can essentially introduce them to the idea of dissipation and degradation. And this way, what you're doing is you're slowly building the idea of energy conservation, because across all these processes, students will see that whenever they think the energy is lost, it in fact is not. It's still there. It's just there in a different form. So this is like a pyramid, right? And if you think about it, like if you go into the pyramid, like you're building a very small pyramid, right, which would correspond to going to energy conservation very quickly, then you have a small pyramid, you can easily tip it over. So it doesn't really provide you with a sound understanding. But then if you have a broad basis and students have learned a lot of about a lot of different forms and how they transform into each other, how they transfer one from one place into another, and they have digged into all of these processes, then you have a much broader pyramid, and that way it's a lot harder to be tipped over. And this corresponds to a much deeper and more thorough understanding of this core concept of energy, right? So we have this idea of an increasingly complex knowledge that underlies these concepts. So what does that mean for teaching not just energy, but teaching physics, right? Because if you think about it, now I've just talked about like, oh, this is a learning progression of energy, right? So how is that helping in building competence over years and not just, like supporting the teaching and learning of energy itself? And here's the idea. The idea is that obviously, across grades 7, 8, and 9, just as an example, this could also be grades 1 to 12, but then the slide would have been cluttered with information. So I'm just focusing maybe on grades 7 through 9, right? And you're teaching all of the areas, the standard areas of physics, electricity, mechanics, thermodynamics, and optics in these grades, right? And then obviously in the context of electricity, you'll talk about electric energy, and in the context of mechanics, you'll be introducing kinetic energy, right? And you can use the idea of energy transformation to bridge between these contents, right? Between these content areas of physics. Essentially what you can do is you can use this idea of transformation once students have learned about it to connect electrical issues or issues related to electricity, current and voltage, to issues in the context of mechanics, right? The voltage that you're applying to a motor and the configuration of the motor in a way determine how fast it can turn, right? Or if you have, you want to, move up a certain load from the bottom into like a top floor of a house, for example, right? You know how much energy you need to do this. So you know how much energy the motor needs to provide, and you can even think, using this idea of transformation, more deeply about things like power. How much power would the motor need to have in order to move this up, right? And as you're doing this, you can introduce thermal energy, right? The students can realize, oh, the motor becomes hot, especially if it works hard, right? It becomes hotter. So obviously some of the electrical energy is actually converted into thermal energy, right? And that way you can also connect thermodynamical phenomena to mechanical and electrical phenomena, right? And you can use the energy concept to bridge between these areas. And then in grade 8, you can pick up on this, right? And you can introduce new forms of energy. You can look at the relationship between electrical energy and potential energy, as I just described. You can look at the proportionality between thermal energy and temperature in order to understand the processes of dissipation and and you can also introduce new forms of energy such as light energy or solar energy, and you can look at transformation processes between electrical energy and light energy, for example, and that can take you to, once you're quantifying these forms of energy, to more thoroughly investigate the process of dissipation and then get to the process of conservation. And I'll show you how. One thing that we've been trying out with a student is to visualize thermal energy that apparently is lost through a thermal imaging camera, right? So if I told you about this interview where you were dropping a stone and then the student would say the energy is gone when the stone lies on the floor. And we did this as an experiment. We have this little piece of cloth and we are dropping a steel ball onto it. But we are doing so by looking at it through a thermal imaging camera. And then what you can see is where the stone hits the cloth, it becomes, there's certain spots where the temperature is higher, you know, where the cloth heats up. And you actually need this piece of cloth because it doesn't work with the ground because the energy is dissipating in the ground too quickly, right? So the energy would have dissipated in too short a time, so you can't really see it. But the cloth is obviously not a good conductor for heat. So you have a longer amount of time, so you can actually in which the energy dissipates. So you can actually see these spots, right? And you, as you can tell, there's multiple spots because the ball is bouncing, right? It's like hitting the ground, it's bouncing back up, and then it kind of like continues to bounce. And we're using this as a starter for students to explore the other processes in which energy seemingly disappears, to learn that whenever they think there's energy disappearing, it actually is not disappearing. It's still available. Well, it's not available, but it's still there, but dissipating into the environment. And then what we are doing is we're setting up an experiment with them where we're intentionally doing this. And we're continuously isolating the system, right? So this is a pendulum that has a, shoot, I don't know the English term. This Wirbelstrombremse is the German thing, right? So you're using the magnetically induced current to kind of slow down the pendulum, right? And what we are doing is we are increasingly building a better isolation of the system. And we're measuring the temperature of the system in every experiment. And what we are seeing with the students is that the better we are isolating the system, the more of the energy we're actually finding, the more of the energy that was originally there. And the interesting thing is what we're doing then is we are getting students to the point where they're themselves concluding. Actually, students at this point will say, well, Mr. Neumann, if we continue doing this, if we would be able to perfectly isolate the system, wouldn't that mean that we get all the energy back? And that is exactly where you would want students to be at, right? Because what they're doing is they're themselves claiming that the concept of energy is that the energy is conserved, right? So that they're formulating the principle I'm sorry, I'm just seeing the question in the chat. I'll get back to that question for Industrial Revolution 4.0 and 5.0 in a minute. Right, so we're getting this back. And students are formulating the energy conservation principle. So brief reflection, where are we? We do have a broad range of learning progressions developed in science and physics in particular for energy, matter, forces and motion. But the question you could answer is, what about the interplay between the concepts, the role of other concepts? That has been solved as well in a way that is called project-based learning. And looking at the watch, I need to speed up a little. So I'll just quickly go through this. The idea is essentially that we're changing learning in a way where we are no longer teaching the students about the knowledge, but we have students do inquiry and develop the knowledge on their own, guided by the teacher, obviously, underneath overarching questions, right? So you could imagine one of these questions being, how can I charge my phone using the sunlight, right? And that has different concepts, matter, energy, and waves that play a role. And then there's more concepts such as systems and system models or energy and matter flows that play a role. And students will combine their knowledge about these concepts to engage in the practices, to ask questions, to develop and use models, and to plan and carry out investigations. And I could go on talking about these units in well, for probably another hour, which I don't want to do at this point. And I just want to highlight that the idea is that students learn about the core concepts, and even concepts that are not just core to physics, but cut across science as they are engaging in the practices. This is generally called an inquiry approach. So the idea is that, based on an anchoring phenomena or problem, students are trying to make sense of the phenomenon or design a solution to the problem. And that is broken down by the teacher. So the teacher is guiding the students in developing, or making sense of that phenomena, or developing a solution to the problem along a sequence of questions about the phenomenon where students more thoroughly investigate the phenomenon using the typical practices of physics, right? What do physicists do? Physicists ask questions, they analyze data, they explain phenomena, and when they have contradicting explanations, they argue about them. And through arguing about different explanations, they are iteratively developing an explanation or to a phenomenon or a solution to a problem. And there is a broad array of evidence showing that inquiry learning, and in particular project-based learning, where you're having these smaller units that are asking questions about real-world phenomena that students engage in, and where students develop the knowledge they're supposed to develop by engaging in developing a solution to a problem. There's overwhelming evidence that this actually supports students in developing a better understanding, and in particular, this integrated competence, right, where they're learning to combine core concepts with other concepts of physics and the practices, and learn how to use these things, their knowledge as well as their abilities and skills together. And the question you could ask is, but what about the third component of competence? What about identity? And the one thing I want to highlight here is, and I'll not go through this into too great detail is that historically, we've been looking at this as a motivation problem, right? So how can we engage students in doing physics? How can we motivate students to do physics? And it's a little bit like getting motivated to go running, right? It's like, well, you hate running, but how can we motivate someone to still do it, right? How can we encourage people? That's not a good way to think about it. A better way to actually think about this is to think about it in terms of identity. We really want students to identify with physics, to think as a physicist, to be a physicist, and to like being a physicist, right? So what students should do is they should perceive physics as something that is part of them, and them being part of physics, right? So only if I think of me as a physicist, I like doing, well, or as a physics person, not a physicist necessarily, but as a physics person, I like doing physics, because if I feel like physics, that's not for me, right? This is oftentimes we hear girls say this, right? Like, oh, physics, that's a boys thing, right? And that's exactly what we don't want. And that's a huge problem, because that's causing that leaky pipeline that we're seeing, where we see an increasing amount of girls dropping out of physics at every stage you could potentially drop out. So what do we know? What could be done? And I'll probably need 6 or 8 more minutes going through this. So in our work, what we've been thinking about is like, okay, what could we do about it, right? Like, how can we help students develop an interest or a physics identity? And we've realized that it's not a problem that's located within the students. It's a problem that is located in the environment. We need to change the environment, so the environment would actually allow students to develop interest, to feel recognized, right? Not just find engaging, interesting, relevant contexts that create their interest, but also enable students to feel recognized, like feel like, oh, I'm recognized doing this, and people say like, oh, look, she is good solving these type of problems, because, well, we all know this, I suppose, and research confirms that very well. When we feel recognized, we feel seen in doing something, we want more of this, and then we continue to engage in this. And the last part is to feel personally competent in this issue, right? So the question is, how can we create a learning environment that is essentially doing this? And we decided, we developed one of these environments in the context of the German physics Olympiad, by not just creating an environment that has motivating and relevant physics contexts, but we also found ways of engaging students in ways in which they feel recognized through cooperative methods, through finding instructors that have a certain positionality, right? Who foster interaction between students, who recognize students, right? So as an implication for teachers, it's really, really important for teachers to recognize the students. We tried to attend to this issue of gender, which is a huge issue in Germany, at least, by creating groups in which there were critical numbers of girls, right? So it's not just this one girl and then the 6 boys who take over. And we actively engaged physics in students in the process of physics through hands-on experiments that were designed specifically for their level of competence, because then they actually feel competent, right? If you make the environment too hard for them, the problem is that they're struggling developing an understanding. This is the results that I'll skip those details and go to the interim reflection, because I want to highlight one last surrounding issue before we are moving into the question and answers. So in summarizing, right, we do have the learning progressions. We do know how to teach students based on these learning progressions. We know that engaging them in the practices to construct the knowledge is supporting the development of competence. We know that project-based learning is effective. We know that project-based learning, together with creating an interesting, recognizing and supportive environment for students, is helping them developing a physics identity. So we need to change how we teach in class, right? In many ways, but we know how to do this. We know how to do this. One of the problems we are having, and that's been highlighted in the chats already, is there's almost no research at this point, and I think that is one important direction for future research, is, does this competence that we're talking about, the competence that is defined in many countries by the respective educational standards, is that actually the competence that students need to be prepared for college on the one hand, and be prepared as an informed citizen on the other hand? What is potentially missing from these competences? What else would students need in order to be capable of meeting the challenges I've been outlining in the very beginning? And the second question in this context is, everything I've been telling you about at this point is really talking about students as a whole, and designing instruction for students in a classroom as a whole. One thing we're particularly struggling with is providing or supporting all students in developing the competencies that we've been talking about, right? In many countries, we are seeing a distribution of students, and this distribution of students is a huge problem, right? Because there's always this like 10 or 20% of the students who just struggle in understanding this, and right now what is missing is a good means of how we can support students in developing this the envisioned levels of understanding, how we can individually support students.
Prof. Neumann?
Yeah. Yeah.
One more minute maybe for presentation before we go to the question and answer session.
Yes, I'll skip the last point.
Okay,
I just realized.
okay.
So don't worry. I know there's don't worry. I'll skip the last part, because essentially there's just one point I want to make about the last part, and that is, when we are talking about these issues that I've just been talking about, we need to take into account the teacher. You know, the one of the most important surrounding issues is the role of the teacher, and the extent to which we are preparing the teachers in training to actually teach physics the way I've just been outlining it should be taught, and to think about teaching physics in a context that looks at preparing students for these great challenges, and not just teaching them physics. I'll skip the details of what I was going to tell you about the teacher, and conclude at this point that I think when we are looking forward, and I've been talking about what has been done, because it's a lot harder to talk about what has not been done. So based on what is done, I do think, and I'm confident to say, we do know a lot from physics education research in order to prepare the teaching and learning of improve the teaching and learning of physics as it is. However, there's a few things that need to be addressed in future research. And the first thing that needs to be addressed is what we are teaching right now, even if we're focusing on the core concepts and the practices of physics, is that really preparing students for college? I would say yes, but there's very little evidence for this. And more importantly, what else do students need to be a critical or be a good and educated citizen? What is missing? I think that is a pressing question that we need to address in future research. The second thing is we do know a lot about how to develop the competence in physics. We have learning progressions for core concepts, for core practices. We have approaches to how we should teach physics and how students should learn physics based on these progressions. What we are missing is research that would help us to learn how we can equally support all students in developing the competence needed. And as a last point, the question is, we should not neglect the teacher as a means to develop that competence. And we need to focus more closely on what do teachers need to know in order to teach this. And we should not neglect this, develop the enthusiasm. Because right now we're very focused on what teachers need to know in our research. And there's almost no research on how we can support teachers and being enthusiastic and supportive about the teaching. Thank you very much for your attention. I'm sorry that I took a little longer. It's a lot harder when you don't see the audience to keep in time and take the right speed. I'm open for questions.
Okay, no problem, Prof. Neumann. Thank you very much. It is a great presentation. So there are 3 questions in the chat box. First from Dr. Ketang Wiono. The question is, dear Prof. Neumann, what are the fundamental changes in physics learning in the 21st century? Then, what kind of basic competencies are needed for the 21st century, especially the Industrial Revolution 4.0 and Society 5.0? Please, Prof. Neumann.
Yeah, I'll try to make this short because I think there's more questions. I'll start with the last question. I actually think we're all there for the industrialization or Industrial Revolution 4.0 and 5.0. Well, the Industrial Revolution 4.0. So what students are learning, at least from a physics point of view, what students are learning in physics, the core ideas of physics, I think we're going the exact right direction, right? We're reducing the amount of content. We're focusing on the core concepts that are especially important: energy, matter, waves, that kind of like touches upon information technology in later grades, right? So we are preparing students to understand the physics of the 21st century. There's a little more work to go, but I think we're going into the right direction. In terms of the Society 5.0, I think it's not just enough to understand the physics. We need to better support the students to understand how physics plays out in the real world. That includes, for example, not just understanding the general ideas behind physics, but also how scientific knowledge is communicated, and particularly in the 21st century, the role of the media plays as a mediator between the scientists and the citizens, right? Because I think one of the problems is the scientists know their business and their stuff, right? And they're communicating it, but then it gets picked up by the media, and the media make a fuss about it. And oftentimes what the media like is they like controversials, right? So what they're trying to find is they think about climate change, right? The overwhelming majority of scientists across the world agrees about the assessment of climate change, the reasons for climate change, the mechanisms underlying this. But there's a few people who disagree, and the media like to highlight those because it kind of like gives you a better selling point, right? So I think we need, as additional competencies, we need students to not just be competent in physics, but understand how physics plays out in society, where it matters, how it matters, and how information is communicated, to understand, like recent developments in physics.
Okay. The second question from Dr. Cristiono, I think almost the same about the learning in 21st century. And then I think from Professor Ida, Prof. Ida, about the climate change. Prof. Neumann, I'm interested in developing research of climate change. Can you provide example of concepts, materials that can be developed in the field of physics education or physics? And I need an instrument to measure of belief of behavior teachers toward climate change. Do you have it? This is special ask from Prof. Ida.
Yeah.
Prof. Neumann, please.
Yeah. I think there were other questions in between, but I think we can cycle back to them. Again, I'll try to make it as short as I can without not giving you a reasonable answer. So first of all, there is a larger group at the IPN that is specifically working on climate literacy, and I would suggest you go online and do some research on what they are currently working on. The project is spearheaded by the biology department, the Department of Biology Education, because obviously climate change matters a lot in the context of biology education. They will have examples of this stuff, and they might actually have an answer to the second question. One of the people you want to talk about is Hanno Michel. That's HANNOMICHEL. If you couldn't, like, send me an email and I can send you his contact, and he'll know about the teacher's behavior towards climate change. And if there's a question there, he'll know it. The second thing, to give you examples about climate change and physics, I think the ice albedo effect, right? The whole problem of the ice at the pole caps melting, and how that changes water levels and how that affects life, but also how these ice shields melting kind of like speeds up the process of climate change, because obviously they're reflecting the sunlight back, or historically they're reflecting the sunlight back into space, which they can't do anymore once they are melted, right? So there's the process going on that's speeding up, and that would be one example of where physics plays a major role and physics concepts play a major role. This is something you can address in physics education. Another example would be the as I said, the flows of energy and matter, right? Like, how do air, and I don't know the English, that's making it a lot harder for me, the exact terminology in English, but there's airflows going on, right? And the airflows in our atmosphere, together with the water flows in our oceans, are driving the way our climate behaves. And as they are changing, they're also changing our climate. And I think that's another thing you can cover in physics. It's the hydro dynamics and the dynamics of airflows. So altogether, it's probably just the aerodynamics. Now I have it. It's the aerodynamics and the hydrodynamics of the Earth system that you can cover in physics. And one last sentence about this, really, because we are talking about the teaching and how to change the teaching and learning. I think we need to move out of our silo. I don't know if you noticed, but a lot of what I've been saying in my talk could as well have been said about other areas of science. And I think that is for a reason, because I think we can no longer pretend that physics learning is different from learning concepts in chemistry or biology. Instead, we should change the view, and we should think about like, what are challenging problems that students could be facing at the level at which they are in terms of their competence, right? What would be challenging problems, and then teach them a more comprehensive approach to solving these problems by drawing on their knowledge from biology, chemistry, physics, earth science, and potentially also societal knowledge, right? Think about power structures. I mean, it's not it's not just the physics of the climate system that decide about climate change. There's a whole lot of power and, you know, emerging countries and their right to be an emerging country. I mean, to just one sentence is, you know, think about like China, for example. I mean, how could Germany or the United States tell China, you can't, you know, like industrialize because we messed up and we already, you know, had so many carbon emissions that now you can't do it anymore, right? There's a whole lot of like power structures and equity issues involved in these questions. And I think students will learn and should learn about them side by side by tackling problems that are real world problems that we're facing, obviously in a simplified version, because if a student would be able to solve all the problems we're facing as humans, then the problems wouldn't be that difficult, I suppose.
Okay, maybe just the short answer, Prof. Neumann, from about STEM is your research interest also. From Evelina Astra Patriot to Prof. Neumann, based on your presentation, we can use learning approach of STEM, science, technology, engineering, and mathematics to developing student enthusiasm. If we can, how we use this matter about energy transformation into STEM approach? Thank you.
Oh, I'm not sure I understand the question correctly. I think the way to support students in developing enthusiasm, or I would like to think of it as identity more broadly, is to provide students with a sense not only of, oh, this is relevant to me. Obviously, choosing challenges in our teaching or problems, real world problems, can increase relevance to students. But we all know that there's things that we think are relevant to our everyday lives, but that we don't necessarily want to care about. Think about the money we that ends up being in our accounts every end of the month or beginning of the month, right? I mean, obviously that is relevant to us because otherwise we can't live. But then a lot of us would probably actually rather not care about whether the money comes or not. So we need to find problems that are engaging for students, but it's not just that. It's also making students feel, as I said, recognized and competent, right? And especially, I think, in terms of the challenges we are facing as humans, it's very important for students to experience agency, to have the sense that if I learn physics, if I learn technology, if I learn STEM more broadly, right? If I engage in STEM, I have a chance to be part of the people that can solve these problems. And that's how we need to engage students, I think. And that's why I think project-based learning, where you have students working with each other on real world issues, real world problems that you're obviously simplifying because obviously they're not that competent yet, but that give them an idea of, oh, if I learn more about it, I will get to the point where I can actually address and solve these issues, or be part of the team or a team that can address some of these issues or solve some of these issues. That, I think, will help students become enthusiastic about doing this. And when we talk about energy transformation, I mean, you can talk about forms, transformation of energy. We've developed a whole unit that situates the whole learning about energy within a climate change a project, right? Where students are exploring different issues in climate change, in like core mechanisms of climate change. And then once they have developed an understanding of what the mechanisms are and how they're working, we're engaging students in thinking about like what could potentially be done in order to use this mechanism to mitigate climate change. And that is very engaging for students. It is what we find. It's very makes students very enthusiastic about physics, because now they see how physics can help solve some actual problems, right? It is not just about learning how a car goes down a slope or something.
Okay, thank you very much, Prof. Neumann. I think many audience want to ask, but unfortunately, we also come to the end of this session. And thank you for your great presentation and explanation. And also for all audience participants, thank you for your kind attention. And
thank you. And if I just quickly can say this, because I see there's a couple questions in the chat that we didn't have the time to answer. I'm very sorry about this. I think I took too long with my talk. As always, there was so much I wanted to tell you about that I kind of lost track of the time. You can send me your questions by email and I'll be happy to answer them.
Okay, thank you. Okay,
I'll put the slide up with my email address so you can take it down.
Okay.
I'm sorry for interrupting. Go ahead.
Okay, no problem. Thank you very much, Prof. And see you next.
Thank you.
Yeah, see you next
soon.
Okay. Okay.
Thank you. Bye-bye.
Bye. Okay, from me, Suhendri, as moderator. Yeah. Assalamualaikum warahmatullahi wabarakatuh. And now Zoom floor back to MC. Please, Bu Dewi.
Thank you so much, Professor Neumann, for a very amazing presentations. And we know that there are still many questions here in various and we'll have chance for another studium general or journal lectures for the next events. And on behalf of the committee and also the Faculty of Teacher Training and Education, we would like to share a certificate of appreciations or token of appreciations for the Professor Neumann. And let me share the screen first. Okay, thank you so much, Professor Neumann, for your time having this general lectures in the new directions of physics education's research, teaching and learning, and Department of Physics Education's Faculty of Teacher Training and Education's Universitas Sriwijaya. And that's all, everyone, for our general lectures for today. Thank you so much for joining with us, and maybe we'll have another events for the next Studium General, and have a nice day. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Thank you, Prof. Neumann.
Thank you, Prof.
Thank you, Prof. Neumann. Great presentation.
Thank you all. Thank you very much.
I hope we can follow up this activity with another activity. I think like write a publication together and another project.
Yeah, I think so. Yeah.
Okay, thank you for all participants, and I will close the Zoom.
Thank you, Mr. Yusuf.
Thank you.
Well.
Yeah. Sorry, because I'm sick. Thank you, Pak Abdul Hakim, and colleagues from another university. Maybe I can find you here because maybe college from Mula Warman Unsia and then the other university. Thank you for you.